there is a question that has fascinated both physicists and science fiction fans for decades. A question that on the surface seems simple, but which actually forces us to confront the fundamental limits of the universe itself. Which is faster, the speed of light or warp speed? For many, the answer may seem obvious. Warp speed, that iconic concept popularized by Star Trek, that allows spaceships to cross galactic distances in a matter of days or weeks, must naturally be superior to the speed of light, that physical constant we have all heard mentioned in science classes. But this intuition, however comforting it may be for science fiction lovers, completely collapses when we rigorously examine what each of these speeds truly means, how they function according to the laws of physics, and, above all, which one could exist outside of television screens and novels. The speed of light is not simply an arbitrary number that scientists decided was important. It is exactly 299,792.58 kilometers per second in a vacuum, a fundamental constant that appears in practically every equation of modern physics. This speed represents not only how fast light travels, but something much deeper and more fundamental. It is the speed at which causality itself propagates through the universe. It is the absolute speed limit for any information, any influence, any object with mass moving through space. Albert Einstein demonstrated in 1905 with his theory of special relativity that this limit is not a technological restriction that we will eventually overcome with more powerful engines, but an immutable characteristic of spacetime itself, as fundamental as the geometry of the universe in which we exist. What makes the speed of light particularly fascinating and frustrating is that it is simultaneously achievable and unreachable. Photons, the particles of light, travel at this speed constantly, effortlessly, without acceleration, simply because they have zero mass. Any massless particle must travel at exactly the speed of light, neither faster nor slower. It is their natural state of existence. But anything with mass, no matter how small that mass, faces an absolutely insurmountable barrier. As an object with mass accelerates, approaching the speed of light, its effective mass increases, requiring increasingly more energy for each additional increment of velocity. The final increment, the final jump from 99.99% of the speed of light to exactly 100%, would require infinite energy, something that is obviously impossible. It is not that our engines are not powerful enough, it is that the universe itself prohibits this final acceleration. The necessity of warp drive in fiction warp speed, in contrast, was born not from mathematical equations, but from narrative necessity. In 1966, when Gene Roddenberry created Star Trek, he faced a fundamental problem. He wanted the crew of the Enterprise to explore new worlds and civilizations, but the distances between stars are so vast that even traveling at the speed of light, reaching nearby stellar systems would take years, and exploring the galaxy would take decades or hundreds of thousands of years. This would make the episodic narrative Roddenberry imagined impossible, where every week the crew visited a new planet with new adventures. The solution was to invent a propulsion system that somehow circumvented the speed of light limit, allowing trips that took days or weeks instead of centuries. Thus was born the warp drive, a completely fictional device that supposedly distorts the space around it, allowing the ship to move faster than light without technically violating relativity. The ironic and fascinating part is that decades after Star Trek invented the concept of warp, a Mexican physicist named Miguel Alcubierre published an article in 1991 demonstrating that the equations of Einstein's theory of general relativity, the theory that governs gravity, and the geometry of spacetime mathematically allow for a space configuration that would work surprisingly similar to Star Trek's warp drive. The Alcubierre metric, as it is now known, describes a bubble of distorted spacetime, where the space in front of a ship contracts and the space behind expands, effectively moving the ship at arbitrarily fast speeds, without the ship itself moving through local space. This means that it technically does not violate the speed of light limit because the ship is not traveling through space faster, than light. The space itself is moving. But before Star Trek fans begin to celebrate the validation of their favorite fiction, it is crucial to understand that mathematically possible does not mean physically realizable. The Alcubierre metric requires something called negative energy or exotic matter, substances with properties that have never been observed and that likely violate fundamental principles of quantum physics. The original calculations suggested that creating a warp bubble would require more negative energy than the entire mass energy of the observable universe. Later, refinements have reduced these requirements to something more modest, perhaps only the mass energy of Jupiter, but this remains completely prohibitive, considering that we do not even know if negative energy exists in the necessary quantities. The warp drive remains for now firmly in the realm of mathematical speculation without physical realization, comparing reality and speculation. So we face a peculiar situation where we must compare two fundamentally different concepts. The speed of light is real, measurable, constantly observed, and backed by more than a century of rigorous experimentation that confirms the predictions of special relativity with extraordinary precision. Particle accelerators routinely accelerate particles to more than 99.99% of the speed of light, and the behavior of these particles perfectly matches relativistic predictions. We have measured time dilation using atomic clocks on airplanes, confirming that time genuinely runs slower for moving objects. The speed of light is not speculative theory. It is experimentally verified reality millions of times over. Warp speed, on the other hand, is a mathematical extrapolation based on physics that may be correct, but requires ingredients that probably do not exist, at least not in the necessary quantities. That is why I invite you to subscribe to Scientia Nocturna, because on this journey, we will explore not only which of these speeds is technically faster, but what each one truly means, according to the laws of physics. What are the practical consequences of traveling at relativistic speeds? How did the concept of warp evolve in Star Trek and other works of science fiction? And above all, which of these two concepts has any possibility of being achieved by humanity? We will calculate travel times, analyze relativistic effects, examine the physics of the Alcubierre drive, and honestly confront the question of whether we can ever move faster than light. In the end, we will have an answer, grounded in physics and engineering, not in desires or fantasies, about which speed truly wins in this competition between reality and fiction. The competition we are about to analyze is not simply about numbers about how many kilometers per second each propulsion method can achieve. It is about the fundamental limits of what is possible in our universe, about the tension between our desires to explore the cosmos and the inflexible restrictions that physics imposes on that desire. It is about why science fiction needs to invent ways to circumvent the speed of light, and why real physics tells us that such evasions are likely impossible. It is, ultimately, about confronting the possibility that the universe is designed in such a way that interstellar distances will forever remain practically insurmountable barriers, no matter how much our technology advances. But it is also about exploring whether, hidden in the equations of general relativity, there is a narrow loophole that could eventually allow us to achieve what Star Trek imagined nearly 60 years ago. The absolute barrier of special relativity. To truly understand why the speed of light represents such an absolute barrier, we must delve into the revolutionary ideas that Albert Einstein presented in 1905 with his theory of special relativity. Before Einstein, physicists assumed that space and time were absolute, existing independently, and providing a fixed stage where events occurred. It was thought that velocities simply added up. If you walked forward on a moving train, your speed, relative to the ground, was the speed of the train, plus your walking speed. This intuitive view of the universe worked perfectly well for everyday speeds, but began to show cracks when physicists tried to apply it to light. Experiments showed that the speed of light was the same, regardless of how you moved relative to the light source, something that seemed to violate common sense, but was consistently verified experimentally. Einstein took this puzzling observation and built upon it a new physics based on two fundamental postulates. The first established that the laws of physics are the same in all inertial reference frames, which means that there is no absolute state of rest in the universe. The second, more radical, postulate affirmed that the speed of light in a vacuum is the same for all observers, regardless of their relative motion. This second postulate seems to violate everyday logic. If you travel toward a light beam at half the speed of light, you would intuitively expect to measure the light traveling at only half its normal speed relative to you. But Einstein showed that you would measure exactly the same speed of light as someone at rest. For this to work, something else must change, and that something is space and time themselves. The consequences of these postulates are profound and counterintuitive. Einstein demonstrated mathematically that as an object accelerates, time for that object runs slower compared to stationary observers, a phenomenon known as time dilation. Simultaneously, the object contracts in the direction of its motion, an effect called length contraction. And perhaps most important for our discussion, the effective mass of the object increases, requiring more and more energy to continue accelerating it. These are not effects that we can ignore or overcome with better technology. They are direct consequences of the structure of spacetime. At everyday speeds, these effects are so minuscule that they are imperceptible, but at speeds close to light, they become dominant and impossible to ignore. Time dilation is particularly fascinating and has been experimentally verified with extraordinary precision. At 10% of the speed of light, time runs approximately 0.5% slower for the moving object, a small but measurable difference with modern atomic clocks. At 50% of the speed of light, time slows down approximately 13%. At 90% of the speed of light, time runs less than half as fast, and at 99.9% of the speed of light, time for the traveler runs at only 2.2% of the normal rate. This means that a traveler moving at this extreme speed would experience approximately 2 weeks of subjective time for every year that passes in the stationary reference frame. It is not magic or science fiction. It is the geometry of spacetime confirmed by decades of experimentation. Length contraction is equally dramatic at relativistic speeds. From the traveler's perspective, moving at 99.9% of the speed of light, distances in the direction of travel contract by the same factor as time dilation. A trip that would normally cover 4.2 light-years to Proxima Centauri would, from the traveler's perspective, cover only approximately 0.09 light-years due to the contraction of space between Earth and the star. This creates a peculiar situation where the traveler and observers on Earth disagree about distances and about the time elapsed, but both perspectives are equally valid within their own reference frames. There is no contradiction because space and time are not absolute but depend on the observer's motion. The infinite energy barrier. But the most problematic effect for real propulsion is the relativistic mass increase. As an object accelerates, its resistance to further acceleration increases as if its mass were increasing. At 50% of the speed of light, the effective mass is approximately 15% greater than the rest mass. At 90%, it is more than double. At 99%, it is more than 7 times greater. And as we get closer and closer to the speed of light, the effective mass approaches infinity. This factor appears in practically all equations of special relativity and quantifies how much time dilates, how much length contracts, and how much effective mass increases at a given speed. The Lorentz factor is one when an object is at rest and grows toward infinity as the velocity approaches the speed of light. There is no way to avoid or cancel this factor. It is directly derived from the fundamental postulates of relativity and has been confirmed in countless experiments. Modern particle accelerators routinely accelerate protons and electrons to speeds where the Lorentz factor is thousands or even millions, and the behavior of these particles perfectly matches relativistic predictions. What makes the speed of light barrier particularly frustrating is that it is not like previous technological barriers that we eventually overcame. It is not like the sound barrier, which was simply an engineering challenge that we solved by designing aircraft with appropriate shapes and sufficiently powerful engines. The speed of light barrier is a fundamental characteristic of spacetime itself, as immutable as the fact that circles have 360 degrees, or that triangles in Euclidean geometry have angles that sum to 180 degrees. We could build an engine 1,000,000 times more powerful than anything existing, and still could not accelerate matter to exactly the speed of light, because the resistance grows without limit as we approach that speed. Einstein also demonstrated another profound consequence. Not only can we not reach the speed of light, we also cannot exceed it. There is no region beyond the speed of light that we could access if only we could break through the barrier. Special relativity divides the universe into 3 causal regions: objects moving slower than light, subluminal; objects moving exactly at the speed of light, only massless particles; and a hypothetical region of objects moving faster than light, superluminal or tachyons. But this third region is not reachable from the first. An object that starts moving slower than light can never accelerate up to or beyond the speed of light. And if tachyons existed, they could never decelerate to subluminal speeds. The 2 regions are permanently separated by an insurmountable barrier. The fundamental reason why the speed of light is an absolute limit is related to causality, the principle that causes precede effects. If we could send information or matter faster than light, we would create situations where different observers would disagree about the temporal order of events. In some reference frames, the effect could precede the cause, violating the principle of causality and creating logical paradoxes. The universe seems to be structured in such a way that it preserves causality, making communication, or travel faster than light, impossible. The speed of light is not simply an arbitrary speed limit. It is the mechanism by which the universe ensures that time has a consistent direction and that cause and effect remain logically ordered. Breaking this barrier would not only require infinite energy, it would require breaking the logical structure of reality itself. The practical limits of relativistic travel. Let us imagine for a moment that we have achieved the impossible. We have built a ship capable of accelerating to 99% of the speed of light, a speed so extreme that relativistic effects completely dominate the travel experience. What would the crew of such a ship actually experience? What would they see when they looked out the windows? How much subjective time would pass during an interstellar journey? And perhaps more importantly, how far could they travel in a human lifetime? These questions allow us to explore the practical consequences of traveling at relativistic speeds and understand why, even approaching the speed of light, although theoretically giving us access to impressive distances, still leaves us confined to an infinitesimal fraction of the cosmos. At 99% of the speed of light, the Lorentz factor is approximately 7, which means that time for the crew runs 7 times slower than for observers on Earth. A trip to Proxima Centauri, our nearest stellar neighbor at 4.2 light-years away, would take approximately 4.2 years, according to Earth clocks. But the crew would experience only approximately 7 months of subjective time. This seems promising until we consider the necessary acceleration and deceleration. Assuming a constant acceleration of 1g, approximately Earth's gravity, to maintain comfort on board, it would take almost 1 year to reach 99% of the speed of light, and another 1 year to decelerate upon arrival. The total trip from the crew's perspective would be approximately 2.5 years, still manageable within a human lifetime. But from the terrestrial perspective, approximately 6 years would have passed. The view from the windows of a ship traveling at such extreme speeds would be profoundly strange and beautiful. Due to relativistic aberration, an effect where the apparent direction of light changes due to the observer's motion, stars ahead of the ship would appear to concentrate into an increasingly smaller region directly ahead, while stars to the sides and behind would shift forward into the visual field. At 99% of the speed of light, practically the entire visible stellar sky would be compressed into a circle of approximately 16 degrees in diameter directly ahead of the ship, leaving the rest of the sky almost completely black, except for the faint cosmic background radiation. The stars in this compressed region would also show extreme Doppler shift. Those directly ahead would be blue shifted, increasing their frequency, while any light coming from behind would be red shifted. But stellar aberration is not the only strange visual effect. At such high speeds, the cosmic microwave background radiation, normally invisible because it is too cold and long wavelength, would Doppler shift into visible frequencies in the direction of travel. The crew would see a brilliant blue glow directly ahead, caused by this shifted background radiation with apparent temperatures of thousands of degrees. Simultaneously, the interstellar medium, though extremely tenuous, would become a constant stream of high-energy particles bombarding the ship. Every hydrogen atom, every dust particle would become high-energy radiation from the ship's perspective. This constant bombardment would require massive shielding, adding weight that in turn requires more energy to accelerate, perpetuating the vicious cycle that plagues all relativistic ship designs. The confinement of relativistic travel let us now consider what distances would be achievable in a human lifetime, traveling at 99% of the speed of light. Assuming a young crew member of 25 years is willing to dedicate 40 years of subjective time to interstellar travel, and taking into account the time needed for acceleration and deceleration, they could reach destinations approximately 280 light-years away. This puts approximately 2,000 stellar systems within their reach, an impressive fraction considering it represents a sphere of 560 light-years in diameter. But this sphere, although containing thousands of stars, represents only an infinitesimal fraction of our galaxy. The Milky Way galaxy is approximately 100,000 light-years in diameter and contains between 200 billion and 400 billion stars. Our achievable sphere of 280 light-years in radius contains approximately 0.002% of the galactic volume. The situation becomes even more restrictive when we consider that these trips are unidirectional in practical terms. If a crew member travels to a system 200 light-years away, they will experience 40 years of subjective time. But on Earth, approximately 280 years will have elapsed. Everyone they knew will be dead. The civilization they left will have evolved in unpredictable ways. If they try to return, 560 years will have passed on Earth. When they arrive back, more than half a millennium. There is no way to avoid this temporal desynchronization. It is a direct consequence of relativistic time dilation. Travelers at near-light speeds effectively become time travelers to the future, able to leap forward in time, but never to return to the present they left. Increasing the speed to 99.9% of the speed of light improves the situation only marginally. At this speed, the Lorentz factor is approximately 22, which means that time runs 22 times slower for the crew members. A trip to Proxima Centauri would take only approximately 2 months of subjective time, plus acceleration and deceleration, perhaps 8 months total. Our 40-year traveler could now reach systems approximately 880 light-years away, expanding the achievable sphere to approximately 15,000 stellar systems. This is significantly better, but still only 0.006% of the galactic volume, and the Earth would have aged 880 years during the outbound journey, making the return even more absurd in terms of temporal desynchronization. The fundamental reality is that even at speeds incredibly close to the speed of light, where relativistic effects are extreme and completely dominate the experience, the universe remains vast beyond comprehension. Reaching the center of our galaxy, approximately 26,000 light-years away, would take 26,000 years, according to Earth clocks, even traveling exactly at the speed of light. For the crew, due to extreme time dilation, at speeds so close to light, the journey could be bearable perhaps only years or decades of subjective time, but they would return to an Earth that has aged 52,000 years, longer than recorded human civilization has existed. Every journey becomes a one-way leap into the distant future, making anything resembling traditional exploration, where explorers return to report their findings, unviable. And this is only within our galaxy. The Andromeda Galaxy, our closest galactic neighbor, is 2.5 million light-years away. Reaching it would take 2.5 million years at the speed of light. The crew, traveling at 99.99% of the speed of light, might experience the trip as only decades due to extreme time dilation, but they would return to an Earth that has aged 5 million years, a period during which entire species have evolved and become extinct. The most distant galaxies we see with telescopes, billions of light-years away, are permanently and irrevocably beyond any physical reach, regardless of what relativistic speeds we achieve. The observable universe contains approximately 2 trillion galaxies, but practically all are forever out of our physical reach, even if we could travel at arbitrarily close to the speed of light. The sober conclusion is that even if we overcome all the monumental technological obstacles to accelerating ships to relativistic speeds, obstacles that include energies equivalent to the total production of entire civilizations, shielding against radiation that might be physically impossible, and life support systems that must function perfectly for decades without maintenance, we still remain confined to a microscopic bubble around our Sunday. The speed of light gives us theoretical access to our immediate stellar neighborhood, perhaps the closest few thousand stars, if we are willing to sacrifice centuries or millennia of Earth time for each trip. But the vast majority of our galaxy, and practically the entire universe beyond, remains as inaccessible as if we were confined to chemical rocket speeds. The speed of light is not fast enough to make the universe our home, and this realization is what led science fiction writers to invent alternatives like warp speed. The narrative invention of warp drive in the summer of 1964, a television writer and producer named Gene Roddenberry began to develop a concept that would forever change television science fiction. His vision was ambitious: to create a series that explored not only outer space, but also philosophical, moral, and social issues through the adventures of a diverse crew aboard a starship. But Roddenberry faced a fundamental technical problem that threatened to make his narrative completely unviable. The distances between stars are so vast that even traveling at the speed of light, the episodic exploration he imagined would be impossible. If the Enterprise traveled at realistic speeds, each episode would cover years or decades of travel time, eliminating any possibility of weekly adventures on new worlds. The solution that Roddenberry and his writers invented not only solved this narrative problem, but created one of the most iconic concepts in science fiction: the warp drive. The term warp, which in English means to bend or distort, was specifically chosen to suggest that the ship somehow bent or distorted the space around it instead of simply moving through it at high speed. This distinction was crucial because it allowed the writers to claim that they were technically not violating Einstein's relativity, which states that nothing can move through space faster than light. If space itself was moving, or if the ship existed in some kind of distorted spatial bubble, then perhaps it could achieve effective speeds greater than light without technically traveling faster than light through local space. It was an elegant, conceptual loophole that allowed rapid travel while paying nominal respect. Known physics, the evolution of the warp scale. Although the specific details of how the warp drive worked remained deliberately vague during the first seasons of the original series, Star Trek established a warp scale where speeds were designated by warp factors: warp 1, warp 2, warp 3, and so on. In the original series, which aired from 1966 to 1969, the relationship between warp factor and effective speed was relatively simple. Speed was the warp factor raised to the power of 3 multiplied by the speed of light. This meant that warp 1 was exactly equivalent to the speed of light. Warp 2 was 8 times the speed of light. Warp 3 was 27 times the speed of light, and so on. Warp 6, a common cruising speed for the Enterprise, represented 216 times the speed of light, allowing the ship to cross light-year distances in days or weeks. This scale provided the narrative flexibility Roddenberry needed while maintaining some internal consistency in how long trips between different destinations took. However, this simple cubic scale created problems at higher warp speeds. Warp 9, occasionally used in emergencies, represented 729 times the speed of light, while warp 10 would be 1,000 times the speed of light. The writers realized that they needed some kind of upper limit to prevent captains from simply jumping to warp 15 or warp 20 whenever they were in a hurry. The narrative solution was to establish that there were technical difficulties and dangers associated with extremely high warp speeds, making warp 9 practically the safe maximum for Federation ships. This provided dramatic tension. Captains had to balance the urgency of situations with the risks of exceeding safe speed limits, while preventing warp speeds from becoming arbitrarily high and eliminating all sense of distance in the galaxy. When Star Trek: The Next Generation debuted in 1987, the producers decided to completely redesign the warp scale to address inconsistencies that had accumulated over decades of various Trek programs. The new scale kept warp 1 as equivalent to the speed of light, but implemented a more complex curve where speeds increased exponentially up to approximately warp 9, after which the curve became asymptotic, approaching but never reaching a theoretical limit designated as warp 10. In this revised scale, warp 9.9 was approximately 1,546 times the speed of light, while warp 9.95 was approximately 2,903 times the speed of light. Warp 10 was redefined as infinite speed, an unattainable theoretical limit that represented being at all points in the universe simultaneously, basically making it the Star Trek equivalent of the speed of light barrier in real physics. This redefinition of warp 10 as infinity created its own narrative problems. In the Star Trek Voyager episode Threshold, the writers explored what would happen if someone actually reached warp 10, resulting in one of the most universally criticized episodes of the entire Trek franchise, where the character who reaches this impossible speed undergoes an accelerated and absurd biological evolution. The episode is generally considered non-canonical by many fans, due to how dramatically it violated both scientific logic and the internal consistency of the Trek universe. But it demonstrated an important point. Even within science fiction, there are limits to how fast you can make ships travel before the narrative consequences become absurd. If you can instantly be anywhere, you eliminate distance, travel, and consequently, drama. The different Trek series also introduced variations and alternatives to the standard warp drive. Star Trek Deep Space Nine featured the Bajoran wormhole, a stable tunnel through space that connected the Alpha Quadrant with the distant Gamma Quadrant, allowing instantaneous travel across 70,000 light-years. Star Trek Voyager, whose central premise was a ship lost 70,000 light-years from home, established that even at sustained maximum warp speeds, the return journey would take 75 years, providing the time frame for the entire series. These concepts expanded Trek's toolkit for dealing with galactic distances while keeping the warp drive as the fundamental propulsion method for routine interstellar travel. Each variation served specific narrative purposes while reinforcing the central idea that space is vast and that even with advanced technology, crossing it requires time and effort. The fascinating thing about the evolution of the warp concept over the decades is how it became increasingly sophisticated in its attempt to sound scientifically plausible while serving narrative needs. Later, Trek writers introduced concepts like subspace distortion fields, subspace geometry, and warp mechanics that paid homage to nascent ideas in real physics, such as higher dimensional spaces and non-Euclidean geometry. Warp technology was described as creating a bubble of distorted spacetime around a chip, contracting the space ahead and expanding it behind a concept that surprisingly anticipated the Alcubierre metric that a real physicist would publish years later. This convergence between fiction and speculative scientific theory demonstrated that, while Star Trek invented warp out of narrative necessity, the writers had instinctively gravitated toward one of the few ways that theoretical physics suggests it might be possible to circumvent the speed of light limit. The warp drive became much more than a simple plot device. It became the defining symbol of Star Trek and the technological optimism of science fiction in general. It represented the idea that apparent limits can be transcended through ingenuity and innovation, that the universe is open to exploration if we are intelligent enough to find the loopholes in the laws of physics. It inspired generations of scientists and engineers who grew up watching Star Trek and decided to dedicate their lives to making the future, the series imagined, real. When Miguel Alcubierre published his article on the warp metric in 1991, he explicitly acknowledged that Star Trek had inspired his work. A concept invented purely to solve a television script problem had fed back into real theoretical physics, creating a fascinating circle where fiction inspired science, which in turn partially validated the fiction. But as we will explore, something being mathematically possible in equations does not make it physically realizable in reality. The Alcubierre metric, mathematical possibility. In 1994, the previous reference to 1991 was a typo in the original text. The actual publication was in 1994. The Mexican physicist Miguel Alcubierre published an article titled "The Warp Drive: Hyperfast Travel Within General Relativity," which demonstrated something extraordinary. Einstein's field equations, the very equations that govern gravity and the geometry of spacetime, mathematically allow a configuration that would work surprisingly similar to Star Trek's warp drive. The Alcubierre metric, as it is now known, describes a solution to Einstein's equations where a region of space, a bubble containing a spaceship, can move at arbitrarily fast speeds without the ship itself moving through local space. This technically avoids the speed of light limit because the ship remains at rest relative to the space immediately around it, while that space itself moves through the surrounding space. It is a subtle, crucial distinction that transforms what would seem like a blatant violation of relativity into something permitted by the theory's mathematics. The conceptual mechanism behind the Alcubierre metric is elegant, though profoundly counterintuitive. Imagine spacetime as an elastic surface that can be stretched and compressed. Alcubierre's warp drive would contract spacetime in front of the ship while simultaneously expanding it behind, effectively creating a wave in the fabric of space that carries the ship forward. Inside the bubble, spacetime remains flat and undistorted, allowing the crew and all equipment on board to experience normal conditions without extreme forces or relativistic effects. The ship does not accelerate through space in the conventional sense. Rather, space itself moves, carrying the ship with it like a surfer riding a wave. This crucial distinction means that from the ship's perspective, it is never moving faster than the local speed of light, avoiding the prohibitions of special relativity. The mathematics describing this spacetime configuration are complex, but are based on well-established principles of general relativity. Einstein demonstrated that mass and energy curve spacetime, and that this curvature is what we experience as gravity. But Einstein's equations are remarkably flexible, allowing many different spacetime configurations, depending on how matter and energy are distributed. Alcubierre discovered that if matter and energy are distributed in a specific way around a region of space, the equations allow that region to move at superluminal speeds. There is nothing in Einstein's field equations that explicitly prohibits space itself from expanding faster than the speed of light relative to other parts of space. In fact, we know this occurs during cosmic inflation in the early universe and continues to occur on cosmological scales due to the expansion of the universe, the collision with physical reality, exotic matter. However, this is where elegant mathematics brutally clashes with physical reality. The specific type of matter and energy required to create the necessary spatial distortion for an Alcubierre warp drive has extraordinarily exotic properties. Specifically, it requires what physicists call negative energy, or exotic matter, substances with negative energy density that would exert negative pressure or tension. This is not antimatter, which has normal positive energy. It is something much stranger that would violate what are known as energy conditions, requirements that most physicists believe any physical matter or energy must satisfy. In all experimental observations ever performed, we have never detected matter with negative energy density in macroscopic quantities. Quantum effects, such as the Casimir effect, exist, where microscopic and temporary negative energy densities can be observed between conducting plates in a vacuum, but scaling this up to the quantities needed to significantly curve spacetime is a huge and likely impossible leap. Alcubierre's original calculations showed that creating a warp bubble large enough to contain a small spacecraft would require a quantity of negative energy equivalent to the total mass energy of Jupiter, approximately 2 multiplied by 10 to the power of 27 kilograms, converted into this exotic substance. This would already be prohibitive, even if we knew how to create negative energy. But the problem is much worse. Not only do we not know how to create it, but most physicists believe that the laws of quantum physics likely prohibit large quantities of negative energy from existing stably. Later refinements of the concept by other physicists have dramatically reduced the energy requirements. In 2012, Harold White of NASA's Johnson Space Center proposed modifications that could reduce the energy requirements to approximately the mass of Voyager 1, about 700 kilograms. This is a massive improvement, but it still requires 700 kilograms of a substance that probably cannot exist. Causality and navigation challenges. Beyond the negative energy problem, there are additional deep challenges with the physics of the Alcubierre drive. One particularly problematic issue involves causality and the possibility of creating temporal paradoxes. Detailed analyses have shown that certain configurations of warp bubbles moving at superluminal speeds could allow the creation of closed time-like curves, essentially loops in time where an object could travel to its own past. Physics generally avoids situations that would allow such paradoxes, suggesting that perhaps additional, yet ununderstood restrictions exist that would make it impossible to create warp bubbles in practice. The universe seems to have built-in protections against causality violations, and these same protections likely prevent the construction of warp drives, even if we could solve the negative energy problem. Another fundamental challenge is control and navigation. Theoretical analyses have shown that once a warp bubble is active and moving, the occupants inside the bubble are causally disconnected from the external universe. They cannot send signals forward outside the bubble to adjust their trajectory, because those signals would never catch up to the front of the bubble, which is moving faster than light. This means that the entire trajectory would have to be programmed before activating the warp drive, with no possibility of mid-course correction. Any unexpected obstacle, any error in the initial calculations, and there would be no way to compensate from within the bubble. The ship would simply continue on its predetermined trajectory until the bubble collapsed, potentially with catastrophic consequences. Further studies have revealed that the frontal region of a moving warp bubble would accumulate particles from the interstellar medium as it travels. When the bubble finally deactivates, upon reaching the destination, these accumulated particles would be released in a burst of extremely high-energy radiation, directed forward. This effect, analogous to an extreme version of the relativistic Doppler shift, would effectively turn the arrival of any warp ship into a potentially destructive event that could sterilize the destination planetary system. To mitigate this problem would require ways of dissipating or redirecting the accumulated energy in manners that we currently do not understand, and which may be impossible within the constraints of warp bubble geometry. The warp drive could technically function as a propulsion system, but inadvertently serve as a weapon of mass destruction every time it is used. The sober reality is that while the Alcubierre metric is mathematically valid as a solution to the Einstein equations, it probably represents what physicists call a solution without physical realization. It is similar to equations that have solutions involving imaginary numbers or infinities, mathematically consistent, but without counterparts in the real physical world. General relativity is an extraordinarily successful theory that has been confirmed by innumerable experiments, but it is not the final theory of gravity. A complete quantum theory of gravity that consistently combines quantum mechanics with general relativity will probably impose additional restrictions that rule out exotic configurations such as warp bubbles. The Alcubierre warp drive remains what it is, a fascinating mathematical curiosity that demonstrates how strange spacetime can be under general relativity, but almost certainly not a viable path toward practical interstellar travel. Star Trek invented warp out of narrative necessity, and physics may allow it in mathematical principle, but reality probably prohibits it in practice. Now that we have explored both the physics of the speed of light and the concepts behind the warp drive, we can finally address a direct comparison that reveals surprising differences. Let us begin with the most basic comparison: Warp 1 versus traveling exactly at the speed of light. In the Star Trek warp scale, Warp 1 is defined as equivalent to the speed of light, 299,792 kilometers per second. This means that, theoretically, a starship traveling at Warp 1 would cover exactly the same distances in the same times as a photon traveling through empty space. In this specific case, there would be no practical difference between the two methods of travel in terms of absolute velocity, although the underlying mechanisms would be completely different. One would involve conventional acceleration through space. The other would involve distortion of space itself. However, this is where the fundamental differences between the two concepts become apparent. Traveling at the speed of light through conventional acceleration, as we have explored, is impossible for any object with mass because it would require infinite energy. Only massless particles like photons can achieve this speed, and they do so instantaneously, without the need for acceleration. An object with mass can approach the speed of light arbitrarily closely, let us say 99.999%, but it can never reach exactly 100%. Warp 1, in theory, avoids this restriction completely because the ship is not accelerating through space to the speed of light. Space itself is moving, carrying the ship at an effective velocity equivalent to the speed of light. This technical distinction is what allows warp to function in principle without violating relativity. Let us consider a concrete journey to Proxima Centauri, our stellar neighbor, 4.2 light-years away. A ship, traveling exactly at the speed of light, if such a thing were possible, would take 4.2 years, according to terrestrial clocks, to complete the journey. There would be no time dilation for the occupants, because at the speed of light, time effectively stops from their perspective, though this is purely theoretical, since objects with mass cannot reach this velocity. A ship at Warp 1, according to Star Trek canon, would also take 4.2 years for the same journey, but crucially, time would pass normally for the crew. There would be no relativistic effects, no time dilation, no length contraction. The crew members would experience 4.2 years of subjective time, exactly equal to the time elapsed on Earth, because inside the warp bubble, space-time remains flat and undistorted. This absence of relativistic effects in warp travel is one of its greatest theoretical advantages over travel at near light speeds using conventional methods. Recall that traveling at 99.9% of the speed of light results in a time dilation factor of approximately 22, meaning that 4.2 terrestrial years would correspond to only approximately 2 months of subjective time for the travelers. This might seem like an advantage, allowing the crew members to experience shorter journeys, but it creates the massive problem of temporal desynchronization with the world of origin. With Warp 1, no such desynchronization exists. A 5-year journey at Warp 1 means 5 years for everyone, both crew and people at home, allowing for consistent communication and coordination without the complications of different relativistic timeframes. However, we must confront the reality that Warp 1, while sounding impressive, is still desperately slow for practical galactic exploration. At Warp 1, crossing our galaxy from one end to the other would take 100,000 years. The entire duration of the galactic diameter, measured in light years, converts directly into years of travel time. Reaching the Virgo galaxy cluster approximately 65 million light-years away, would take 65 million years. Even within our immediate stellar neighborhood, missions would take years or decades. A round trip to Barnard's star, 6 light-years away, would take 12 years total, a significant commitment requiring ships designed for long-duration voyages with all the complexity of life support, supplies, and psychological considerations for crews on multi-year journeys. This is precisely why Star Trek rarely shows the Enterprise traveling at Warp 1. Typical cruising speeds are Warp 5 or Warp 6, and emergency speeds reach Warp 9 or greater. Even in the fictional universe of Star Trek, Warp 1 is recognized as insufficient for practical exploration. The writers intuitively understood what the calculations confirm, that even moving at the speed of light, while representing an incomprehensible technological advance over our current capabilities, still leaves us confined to travel times that measure in years or decades for nearby destinations and centuries or millennia for more distant destinations. The galaxy remains vast and inaccessible, even at this speed that seems incredibly fast to us. Now let us compare the energy and technological requirements of each approach. Accelerating a 1,000-ton ship up to 99.9% of the speed of light would require kinetic energy of approximately 5 times 10 to the 21st joules, equivalent to approximately 1,000 megatons of TNT, or about 20,000 times the energy of the most powerful bomb ever detonated. This is astronomical, but at least calculable and based on known physics. Creating an Alcubierre warp bubble, even using the most optimistic estimates that reduce the requirements to only 700 kilograms of exotic matter, requires something that probably does not exist: negative energy in macroscopic quantities. We cannot meaningfully quantify the energy cost of creating something that is likely physically impossible. The engineering challenges also differ radically. Accelerating a ship to near-light speeds requires incredibly powerful engines, probably based on nuclear fusion or matter-antimatter annihilation, systems that we at least understand in principle, even if we cannot currently build them to the necessary scale. It requires massive shielding against radiation and particle impacts, another monumental challenge, but one based on materials engineering that we can conceptualize. A warp drive requires not only exotic energy, which probably does not exist, but also the ability to configure that energy into precise spatial patterns around the ship, manipulating the geometry of space-time itself in ways for which we do not even have clear theoretical concepts of how to achieve. It is the difference between an extremely difficult engineering problem and something that may require completely new physics that we have not yet discovered. The conclusion of this comparison between the speed of light and Warp 1 is that they are conceptually equivalent in velocity, but radically different in physical viability. The speed of light is achievable in principle through conventional acceleration if we could overcome monumental technological hurdles in energy generation, propulsion, and protection. Warp 1 requires not only technological advances, but fundamental shifts in our understanding of physics, the discovery of new forms of matter and energy, and space-time manipulation capabilities that currently seem impossible. Both leave us confined to travel times of years or decades for nearby destinations, revealing that even these extraordinary velocities are inadequate for making the universe our home. This realization is what motivates the higher warp speeds in Star Trek, and what we will explore next. What happens when we increase the warp factor to truly extreme velocities that make the speed of light seem comparatively glacial? In Star Trek, when the Enterprise faces truly desperate emergencies, when every second counts and the fate of the crew or even entire civilizations hangs in the balance, the captain gives the order that every fan recognizes maximum warp. Depending on the era and the warp scale used, this usually means warp 9.9 or even greater velocities, speeds so extreme that they stress the engines to their absolute limits and can only be maintained for brief periods before risking catastrophic damage to the ship. But how fast is warp 9.9 really? How does it compare to the speed of light? that we have been discussing? And perhaps more importantly, do these extreme velocities violate any fundamental principle of physics, or do they remain within the limits of what general relativity might theoretically allow? Under the original warp scale, from the original series of Star Trek, where the velocity was the warp factor cubed multiplied by the speed of light, warp 9.9 would represent 970.3 times the speed of light. This would mean that a trip to Proxima Centauri would take approximately 1.6 days instead of 4.2 years, a dramatic reduction that would convert interstellar travel from a multi-year commitment into a weekend excursion. Under this scale, the galaxy suddenly becomes much more accessible. Reaching the galactic center, 26,000 light-years away, would take approximately 26 years instead of 26,000, entering the realm of a career-long mission instead of a multi-generational project. However, this scale was considered problematic by later Trek writers because it allowed ships to reach arbitrarily high speeds simply by increasing the warp factor, eliminating any real sense of distance in the universe. The revised warp scale, introduced in the next generation, addressed this problem by making warp 10 an unreachable limit, representing infinite velocity. In this scale, warp 9.9 is equivalent to approximately 1,990 times the speed of light, more than double the speed under the original scale. At this velocity, Proxima Centauri would be less than 19 hours away, the galactic center about 13 years, and crossing the entire galaxy from end to end would take approximately 50 years. This still represents substantial travel times for distant destinations, but it converts galactic exploration from impossible to merely extremely challenging. Warp 9.95, occasionally mentioned in absolute emergencies, is approximately 2,903 times the speed of light, reducing these times even further, but approaching dangerously close to the theoretical limit of warp 10. To put these truly astounding velocities into perspective, let us consider what they mean in terms of actual physical movement. At 1,990 times the speed of light, a ship would cross the distance from the Earth to the Sun, approximately 150 million kilometers, in just tenths of a second. It would cross the orbit of Neptune, the outer limit of our solar system, in approximately 2.5 hours. In a single day, at warp 9.9, a ship would travel approximately 5.5 light-years past Proxima Centauri. The scale of velocity is so extreme that it defies intuitive comprehension. We are talking about movement through space, at speeds where the entire galaxy becomes navigable within a human lifetime, where star systems separated by light-years are hours or days apart. Compared to the speed of light, warp 9.9 is not simply faster, it is incomprehensibly faster. A photon traveling from Earth would take 8 minutes to reach the Sun. A ship at warp 9.9 would make the same journey in tenths of a second, approximately 1,000 times faster. Where light takes 4.2 years to reach Proxima Centauri, the ship at warp 9.9 arrives in less than a day. The difference is not like comparing a car to an airplane. It is like comparing a snail to a rocket. The speed of light, which seems so inconceivably fast to us that nothing in our daily experience remotely approaches it, becomes comparatively glacial when contrasted with extreme warp velocities. This is precisely why Star Trek needed to invent warp. Even the speed of light is too slow for the narratives they wanted to tell. Now we must confront the crucial question: do these extreme velocities violate fundamental physics? The answer is nuanced and depends on how we interpret what it means to travel at warp 9.9. If we assume that the ship is moving through space in the conventional sense, then yes, it absolutely violates special relativity, which establishes that nothing with mass can move through space faster than light. But the warp concept, and specifically the Alcubierre metric, which represents the only serious scientific proposal similar to warp, avoids this violation by redefining what it means to move. The ship is not moving through space faster than light. The space itself moves, and the ship is carried within a bubble of flat space. From this perspective, warp 9.9 no more violates relativity than warp 1 does. Both operate under the same principle of spatial manipulation. However, there are limits to how fast even a warp bubble could theoretically move. Although general relativity does not explicitly prohibit regions of space from moving faster than light relative to one another, there are causality restrictions that would probably impose practical limits. If warp bubbles could reach arbitrarily high speeds, it would be possible to create situations where a traveler could send information or even travel to their own past, creating temporal paradoxes. Physics generally avoids such situations, suggesting that there must be some mechanism, perhaps related to the quantum physics of spacetime, that prevents warp bubbles from reaching velocities where causality violations become possible. We do not know exactly where this limit would be, but it probably exists somewhere, perhaps equivalent to only a few times the speed of light, instead of the thousands of times that Star Trek assumes. The requirements for exotic energy also scale dramatically with velocity, while calculations for warp bubbles moving at modest speeds suggest negative energy requirements equivalent to hundreds or thousands of kilograms of mass. Bubbles moving at thousands of times the speed of light would likely require much larger quantities. The geometry of spacetime needs to be distorted more extremely to accommodate higher velocities, requiring more exotic and probably more massive energy configurations. Even if negative energy existed, which is doubtful, there would probably be practical limits to how much could be concentrated and configured before quantum effects or stability considerations made the configuration impossible. Warp 9.9 would probably require not only exotic energy, but quantities and configurations of that energy that violate multiple physical principles simultaneously. There is also the question of what would happen to a warp bubble at such extreme velocities. As we mentioned earlier, even modest warp bubbles would accumulate particles from the interstellar medium in their forward region, creating dangerous radiation when the bubble collapses. At warp 9.9, this effect would be enormously amplified. The bubble would be traversing the interstellar medium at speeds so extreme that even the near-perfect vacuum between the stars would become a constant bombardment of ultra-high energy particles. From the bubble's perspective, the accumulated energy, released when the bubble is deactivated, could be sufficient to sterilize not only planets, but entire star systems. The warp drive would become an apocalyptic weapon, making its use near any destination we wish to preserve impossible. The uncomfortable reality is that warp 9.9, although mathematically definable within the Star Trek framework, and perhaps technically permissible under very generous interpretations of general relativity, almost certainly violates multiple physical principles in ways that make it impossible in practice. It is not just that we do not have the technology, it is that the underlying physics probably prohibits such extreme velocities through mechanisms that we do not yet fully understand. Star Trek can order maximum warp and cross-sectors of the galaxy in days, but real physics probably imposes much more modest limits on any plausible form of superluminal travel, if such travel is possible at all. When we compare warp 9.9 with the speed of light, we are not truly comparing two physical possibilities. We are comparing a fundamental limit of the universe with an elegant mathematical fantasy that will likely forever remain in the realm of fiction. After exhaustively exploring both the speed of light and warp speeds in their various forms, from warp 1 to the extreme velocities of warp 9.9, we can finally issue a scientific verdict on which truly wins in this competition between physical reality and speculative fiction. But this verdict will not merely be a matter of numbers of kilometers per second, but of something much more fundamental. Which of these concepts has any real possibility of existing outside of mathematical equations and television screens? The question is not merely which is faster in theory, but which we could plausibly build, test, and use in the real universe, governed by the laws of physics that we have experimentally verified for over a century. Let us begin with what we know with absolute certainty. The speed of light is real, measurable, and has been verified with extraordinary precision in innumerable experiments for decades. It is not theoretical speculation or mathematical extrapolation. It is an observable characteristic of the universe that we routinely measure and that forms the basis of technologies we use daily. The GPS in your phone must correct for relativistic effects related to the speed of light to function correctly. Particle accelerators accelerate protons and electrons to over 99.9% of the speed of light, and the behavior of these particles perfectly matches the predictions of special relativity. We have measured time dilation using atomic clocks on airplanes and satellites, confirming that time really passes more slowly for moving objects, exactly as Einstein predicted. The speed of light is not theory in the sense of conjecture. It is verified experimental physics down to levels of precision exceeding 1 part in 1 billion. More importantly, reaching velocities close to the speed of light does not require new or exotic physics. We know exactly what is needed: energy, a lot of energy, but conventional energy of the type we perfectly understand. Nuclear fusion, matter-antimatter, annihilation, or even laser propulsion from terrestrial stations are all concepts based on well-established physics. The challenges are ones of engineering and scale, not of fundamental principles. We need to build fusion reactors that work reliably for years, or produce and store antimatter in kilogram quantities instead of nanograms, or build 100 gigawatt lasers. These are monumental problems that could take centuries to solve, but they are engineering problems where we can plot a plausible path from where we are now to where we need to be. They do not require discovering new laws of physics or finding exotic substances that probably do not exist. Warp speed, in contrast, currently exists only in 2 forms: as a narrative device in science fiction, and as a mathematical solution to the equations of general relativity that requires physically implausible ingredients. The Alcubierre metric is mathematically valid. This is not in dispute. But being mathematically valid is not the same as being physically realizable. The mathematics of general relativity allows for many configurations of spacetime that probably cannot exist in reality. Traversable wormholes, time machines, and warp drives all share the common characteristic of requiring negative energy or exotic matter in macroscopic quantities, substances that would violate energy principles that most physicists believe are fundamental to the stability of the universe. The requirement for negative energy is not a minor technical detail that we will eventually solve with enough research. It is a fundamental obstacle that suggests that these exotic mathematical solutions are possible in equations, but prohibited in physical reality. Quantum physics imposes restrictions on how much negative energy can exist and where, restrictions that likely make it impossible to concentrate the necessary quantities in the spatial configurations required for a warp drive. Even the most optimistic estimates that reduce the requirements to only hundreds of kilograms of exotic matter do not change the fundamental problem. We are trying to build something using ingredients that likely cannot exist in the necessary form. It is like trying to bake a cake that requires flour made of imaginary numbers. The recipe may be mathematically well specified, but the ingredients do not exist in the physical world. Beyond the negative energy problem, warp drives face causality challenges that suggest the universe has built-in protections against their existence. Allowing superluminal travel by any means, whether warp or wormholes or any other method, opens the possibility of creating temporal paradoxes where effects precede causes. Physics generally avoids such situations, not for convenience, but because preserving causality seems to be a fundamental organizing principle of the universe. There are theoretical indications that any attempt to create configurations of spacetime that would permit superluminal travel would trigger quantum processes that would destroy those configurations before they could be used. The universe may literally self-censor, preventing the creation of time machines and warp drives through quantum mechanisms that we do not yet fully comprehend, but whose effects we can calculate. When we compare the physical plausibility of reaching near-light speeds through conventional acceleration versus creating warp bubbles, the difference is like comparing climbing Mount Everest without oxygen versus climbing to the moon on a ladder. The former is extraordinarily difficult, requiring extreme preparation, advanced technology, and perfect conditions. But it is fundamentally possible within the known laws of physics. The latter is not simply difficult, it is absurd, violating fundamental principles of how reality works. Reaching 99% of the speed of light requires solving monumental engineering problems, but every problem is of the type that we can clearly conceptualize. Creating a warp bubble requires discovering completely new physics, finding or creating substances that are likely prohibited by the laws of nature, and manipulating spacetime in ways that may be fundamentally impossible. The scientific verdict then is clear, though perhaps disappointing for science fiction fans. The speed of light wins not because it is faster. Warp 9.9 is obviously numerically much greater, but because it is real, while warp probably is not. Near-light velocities are difficult, perhaps so difficult that humanity will never achieve them in practice, but they are possible in principle. Warp velocities are impossible not just for us now, but probably for any civilization, no matter how advanced, because they require violating fundamental physical principles. This is not a limitation of our current technology that we will eventually overcome. It is a feature of the universe itself. The speed of light wins because it exists, because we have measured it, because we understand it, and because, although it is extraordinarily difficult to achieve, it does not require rewriting the laws of physics. This does not mean we will never discover ways to travel faster than light. Physics has been surprising before, revealing phenomena that previous generations could not imagine. But based on everything we currently know, on over a century of experimental physics that has confirmed relativity again and again, on our understanding of quantum mechanics and energy conditions, and on detailed theoretical analyses of proposals like the Alcubierre metric, the honest conclusion is that superluminal travel is probably impossible. The universe seems to be designed in such a way that information and matter are limited to traveling at subluminal velocities, that civilizations are confined to their home star systems, or at least to minuscule bubbles around them, and that the vast distances between the stars will forever remain as practically insurmountable barriers. Star Trek needed warp to tell its stories, but real physics probably will never give us warp, no matter how much we desire it or how hard we work for it. The speed of light wins by default because it is the only thing we truly have, and it is probably all we will ever have. The comparison between the speed of light and warp speed has led us to a conclusion that transcends mere numbers of kilometers per second or velocity factors. What we have discovered is something much deeper about the nature of the universe, about the limits of the possible, and about why science fiction and real science diverge so dramatically when it comes to interstellar travel. This divergence is not accidental. It is not simply that science has not yet caught up to what fiction imagines, but that it represents fundamental differences in their purposes, methods, and constraints. Exploring these differences helps us to understand not only why Star Trek needed to invent warp, but also what this necessity teaches us about human aspirations and the physical realities that confine us. Science fiction, at its best, is not about predicting the technological future with accuracy, but about exploring ideas, social consequences of technology, and the human condition in speculative contexts. Gene Roddenberry created Star Trek, not because he believed that warp drives would eventually be invented, but because he needed a mechanism that allowed his characters to encounter new civilizations and explore moral dilemmas weekly. The warp drive is a narrative device, a convention that the audience accepts so that the real stories, the ones about justice, diversity, ethics, and humanity, can unfold. Criticizing Star Trek because warp violates known physics is like criticizing Romeo and Juliet because people do not speak in iambic pentameter in real life. The point was never technical accuracy, but the exploration of deeper themes, using space as a metaphorical stage. Real physics, in contrast, is constrained by what the universe allows. Physicists cannot simply decide that the speed of light is an inconvenient limit and write equations that ignore it. They must work within the restrictions imposed by experimental reality, by observations that have been verified thousands of times under controlled conditions. When special relativity establishes that nothing with mass can reach the speed of light, this is not an arbitrary choice, but a mathematical consequence of fundamental postulates that have been confirmed with extraordinary precision. Physics cannot simply invent convenient solutions to difficult problems the way fiction can. It must honestly confront the limitations that nature imposes, no matter how frustrating or inconvenient those limitations are for our ambitions of cosmic exploration. This fundamental difference between fiction that can invent what it needs and science that must work with what exists explains why practically all science fiction involving galactic exploration has invented some form of faster-than-light travel. Star Trek has warp. Star Wars has hyperspace. Battlestar Galactica has FTL jumps. Dune has guild navigators who fold space, and so on. Each franchise invents its own version, because they all face the same fundamental problem. Interstellar distances, measured in light years, make it impossible to tell stories of exploration and adventure if ships are limited to subliminal velocities. Even traveling at 99% of the speed of light, crossing the galaxy, would take over 100,000 years. No narrative can function on such timescales without resorting to generational ships or cryosleep, and those concepts introduce their own narrative complications that make it difficult to tell certain types of stories. But there is something profoundly revealing in the fact that virtually all serious science fiction needs to invent FTL to function. It tells us something important about human aspirations and about how these collide with the realities of the universe. Humans are a curious, exploratory species that has spent its history expanding into new territories, discovering new lands, and constantly pushing toward more distant horizons. This exploratory urge is deeply rooted in our psychology and has driven much of our technological and cultural progress. But the universe, indifferent to our desires, has structured space and time in such a way that this exploratory urge hits an insurmountable wall when we try to apply it to interstellar scales. The stars are simply too far away, and the speed of light is simply too slow to permit the kind of exploration that we instinctively desire. The science fiction that invents FTL is not simply conveniently ignoring real physics. It is expressing a deep human desire for the universe to be different from what it is. It is a form of denial, but it is comprehensible and perhaps even psychologically necessary denial. If we were to fully accept that the stars are permanently out of reach, that we will never directly know other worlds beyond our solar system, that the vast universe we see with telescopes will forever remain as images on screens instead of places we can visit, this could be profoundly demoralizing. The science fiction that imagines ways to overcome these limitations provides hope, even if it is hope based on impossible physics. It allows us to dream of a future where humanity is not confined to a single star system, where the cosmos is open to exploration, where our descendants will walk on worlds orbiting distant stars. And there is real value in such dreams, even when we know they are likely impossible. Star Trek inspired generations of scientists and engineers who dedicated their lives to pushing the frontiers of the possible. Miguel Alcubierre developed his warp metric specifically because Star Trek inspired him to wonder if such a thing could be mathematically possible. Although his work probably will not lead to functional warp drives, it has contributed to our understanding of general relativity and the types of space-time configurations that Einstein's equations allow. Science fiction functions as imaginative exploration that sometimes identifies possibilities that can later be investigated scientifically. Most of these possibilities turn out to be dead ends, but occasionally fiction anticipates or inspires real developments. The Star Trek communicator anticipated cell phones, the next generation tablets anticipated iPads, and so on. But we must be honest about the differences between incremental technological innovations like portable phones and fundamental violations of established physics, like faster-than-light travel. The former are plausible projections of existing trends, applications of well-understood physical principles in new configurations. The latter require the fundamental laws of the universe to be different from what a century of rigorous experimentation has shown us they are. We can build better communicators because the principles of electromagnetic transmission are well understood and only need to be refined and miniaturized. We cannot build warp drives because they require negative energy that likely violates fundamental quantum principles. The difference is not one of degree, but of kind. One is advanced engineering, applying known physics. The other is fantasy that requires rewriting the laws of nature. This distinction is crucial because it affects how we think about the future of human space exploration and what realistic expectations we can have. If we assume that we will eventually develop FTL because science fiction constantly shows it, we prepare ourselves for inevitable disappointment. If, instead, we accept that we are likely permanently confined to subluminal velocities, we can focus our efforts on what is genuinely possible. Advanced robotics for exploration via probes, increasingly powerful telescopes for remote observation, and perhaps eventually establishing a human presence on other bodies within our solar system. Mars, the moons of Jupiter, the asteroids. These are challenging but achievable destinations that do not require violating fundamental physics. They represent a more modest but realistic version of the human future in space. The tension between what science fiction imagines and what real physics allows teaches us cosmic humility. The universe was not designed for our convenience or to satisfy our exploratory desires. It is structured according to principles that existed billions of years before we evolved and that will continue to govern long after we have become extinct. These principles are non-negotiable. They cannot be voted out of existence or circumvented through sufficient ingenuity. The speed of light is an absolute limit, not because we have not yet discovered how to overcome it, but because the universe is fundamentally structured in such a way that overcoming it would violate causality itself. Learning to accept this reality, to work creatively within these constraints, instead of perpetually fantasizing about escaping them, may itself be a form of maturity as a technological civilization.